Hello to everybody. Today we will continue with another tool. It's called the Thevenin's theorem. We don't demonstrate this theorem, so in electronics there are theorems that can be demonstrated, of course. Now we just mention it as a method, and we will probably not use it during this course. But it can be important just to mention about this thing because it gives us the possibility to better understand the concept of equivalent circuit. So last time we have spoken about equivalent resistors. We can extend this concept also to circuits, so portion of circuits that behave in a way that the other part of the circuit, external to that portion that we selected, cannot understand that we modified the circuit. For instance, here you have a quite complicated circuit. So we have a voltage generator, a current generator, then another voltage generator here, and 1, 2, 3, 4 resistors. So now we want to ask a question. So you see that here I defined two nodes, A and B. It can be any, but I decided to choose those two ones. So the question is, if I focus my attention on this branch between the nodes A and B, imagine that I can pick up this resistor and elevate it like this, and all the rest of the circuit will be deformed in order to have it still connected. So if I isolate this thing but I leave everything connected and I put all the rest in a black box, can I do something in order to simplify the circuit? Can I use less components, for instance, in a way that the resistor will not understand that I did this simplification? So when I say the circuit will not understand, it means that whatever the circuit can, between commas, see is voltage and current. So if I select a branch between two nodes, so the only two variables that this branch and the component in it, so the resistor in this case R2, can see is the voltage between A and B and the current flowing in it. Can I substitute the rest of the circuit in order to produce the same voltage between A and B and the same current in R2? So this method works this way. So we leave alone the portion of circuit of interest, which means in this case we remove the resistor R2. Then we open all the current sources, which basically means that we have to cut the connections of all current sources. So we remove the current sources. Then it says we have to calculate the equivalent voltage between A and B. Equivalent voltage, it means that if we leave alone the portion of interest, so if we remove this A and B, and if we open the current generators, by using node analysis as we did last time, we can solve the rest of the circuit, and then we know that once we solve the circuit we know all the currents and all the voltages. So we don't do this now, but you can imagine that we can calculate the voltage VAB between node A and B, and we keep this value. We call it V equivalent, which is VAB in our case. Then we short all the voltage sources, which means that we put a bridge like a short circuit, and if you prefer, after this you can also remove the voltage source. And then you calculate the equivalent resistance between A and B. So by calculating the equivalent resistance, it means that we probably have to do some parallels and some series. So for instance, if we are at this point, R3 is in parallel with R4, and then if you carefully inspect the rest of the circuit, so this through this path would be in parallel also to R3 and R4. So with the formulas we studied last time, we can calculate what is the equivalent resistor between A and B. So we call it R equivalent. So the theorem demonstrates, we don't do this now, that if we do this, then we can assemble this circuit here, where we put an equivalent voltage source in series with an equivalent resistor, which is what we called R equivalent, and then we put our component of interest that we removed in order to be able to compute all this stuff. And if we do this, the theorem demonstrates that, okay, this is A and B, the same current will flow in the resistor and the same voltage will be across this resistor, which basically means that we can eliminate most of the things here and we just keep two things with two different values. So this is one method that can be used in order to reduce the number of components in a circuit, or sometimes to analyze some properties. You see something which is very complicated, but if you're interested in one branch of the circuit, all the rest can be summarized with such kind of things. Okay, now before we proceed, we keep this circuit in mind and we speak a little bit about voltage generators. So I want to go back to the scratch notes. So imagine now we have this circuit. Sorry, I want to change color. Okay. A battery, a resistor, and another resistor like this. So V, R, I call it RI, and RL. So let's say that what we want to do now is to take one battery and power up what is called a load. So our load, in an ideal way. So we ideally want to have the same voltage here to be here. So of course, to have this, it means that this other resistor should be 0. But in reality, this cannot be done because batteries have internal resistances. So what I call here Ri. So our real battery, actually, it's like this. Okay, so this is the real battery. So it's different from the ideal case. We cannot eliminate this internal resistance. It's something that has to do, for instance, with the resistivity of the electrolyte inside the battery and such kind of things. So what can we do if we want to have a stable voltage here with a precise value? So in principle we can do this. We can take our real battery with its own internal resistance that we cannot eliminate. Then we put another resistor and then our load, which is the thing at which we want to regulate the voltage. So if we can vary the value of this resistor here in a way that by measuring the voltage here somehow, let's say with a voltmeter, I put this thing here, like this is a voltmeter, and this voltmeter can somehow control the value of this resistor, then assuming that we start from a voltage of the battery which is a little bit greater than what we want to have here, in order to have some margin, because between those two nodes here and here we will have a voltage drop. We know this from the Ohm's law. So if we can control this resistor by what we measure here, then we can regulate the voltage between the nodes A and B of interest. We will see later in this course that this thing is possible, and the device that will allow us to do this is a device which is not a bipole, but it's a tripole. So it has an input, an output and a control terminal. This thing will be the transistor, which is an acronym that stands for transfer resistor. So it's a resistor like this, but we can control it with a control terminal. And the voltmeter that we put here, if we want to do something very precise, is something that we can obtain as the result of the application of what would be called the operational amplifier. Operational amplifier. Also, they say op-amp. So we want to try to understand those kind of things, because those kind of things are the things that transforms real components into ideal components, which are very useful. Okay. So now we have to understand that till this moment we worked only with resistors, but we know that there are also capacitors, at least inductors, and then also other things which are ideal amplifiers. So what's an ideal amplifier? It's a black box. Let's say you have two inputs. Here you put a voltage, V input. We don't know what's inside. And here we have V output. And an ideal amplifier is something that makes V output equals a certain coefficient, let's call it A sometimes called also G, for that stands for gain, multiplied the input, where A is constant. So this thing is called ideal amplifier. It magnifies or reduces the amount of voltage we can read in a so-called port to what we read to another port. So this is the input port and this is the output port. And those objects like this one, black boxes with an input port and an output port, are called two-port networks. Okay, so another important thing, we said that those circuits are linear. For us, it means that we can associate to those circuits the property that they will not change the frequency of their sources, but in case they can only change the amplitude or the phase. So now let's try to extend the concept of resistor to the concept of resistance to the concept of impedance. So we want to be able to define such kind of thing. So the ratio of a voltage and a current in a bipole component, which we know is something similar to the Ohm's law, because if we put this here in a corner, V equals R multiplied I. So R is V over I. Here we call it Z. But this time we want to do this for all possible frequencies. So what we consider is that V is not a constant voltage, but something that depends on omega, and we can write it as a phasor. So here we have a sinusoidal written with the Euler formula. So if we apply the Ohm's law, we take the voltage and we compute the current by simply doing V over R, then we can substitute the value of the current as depending on the frequency omega of the sinusoidal signal with this. And of course this can just be simplified, and we get that the impedance of a resistor, as defined with this definition, doesn't depend on the frequency. So if we apply a sinusoidal signal of voltage to a resistor, then we have across the resistor the same sinusoidal signal and the current according to the Ohm's law. Okay. So nothing changes for resistors if we switch from a constant value to a signal which is time variable. But it's not like this for the other components. So now if we analyze the case of the capacitor, the story is different, because the capacitor is not a resistor, so it doesn't follow the Ohm's law. The constitutive law that connects the voltage to something else in the capacitor is this one. So if we take the voltage across a capacitor, what we can know is that the charge which is deposited on the plates of the capacitor, remember the two parallel plates, is proportional to a certain value C that we called capacitance. So now we have to know that if we consider the charge as a function of time. Why we want to do this? Because if the capacitor is manufactured in a way like this, we don't modify its geometry, then the only thing that we can modify now is the voltage, because we attach the sinusoidal voltage source to the capacitor. Then the charge will change in time, and then by definition the rate at which the charge is changing in time is called the current. So we know those two things. So we use this in order to understand what is the ratio between the voltage applied to a capacitor and the current flowing in a capacitor, like this. So if we just plug those things in, then we can say that the current I here, we get it from the definition of charge. So we take this and we have to compute the time derivative. Now the voltage V is a sinusoidal, like this, written as a phasor, and if we do this here, so time derivative of V e raised to the I omega t, this thing here, let me do it like this, d and dt of V e to the I omega t. So V is the magnitude of this phasor, so it goes out. Maybe you don't see very well, so let me change color, sorry. d over dt V I omega t. So the magnitude of the phasor is constant, so it goes out of the derivative. And then we have to compute the derivative of the exponential, which is the exponential itself, multiplied the derivative of its argument respect to the variable t. So this is I omega e to the I omega t, which is what is written here. So again, we do some simplifications. So this goes away with this, and then we get this. So now we see that the impedance of a capacitor is different from the impedance of the resistor, and also it depends on the frequency, and also it's a complex number. So let's analyze two important cases. What happens if we put the frequency omega equals to 0? We have something like 1 over 0, which is sort of plus infinitive, which means that in terms of voltage and current, it's something like the resistance of a capacitor when we drive it with a constant voltage. Omega equals 0 means a sinusoidal that is not oscillating, basically. It makes the capacitor to be a resistor with an infinitive amount of resistance, which means that if you calculate the current like V equals Ri, and therefore I equals V over R, if R tends to be infinitive, then the current is 0. This means that when everything is steady, there is no current flowing in the capacitor, and we know this because the capacitor is just two plates, one in front of each other with nothing in between. So we expect this thing. The thing that we probably don't expect very well is that if we make omega big, very big, then this ratio tends to 0 instead of tending to infinity, which means that for high frequency a capacitor is a kind of short circuit. So we have to be careful when we design circuits with capacitor and we put high frequency because we have to remember this thing. So the capacitor is also a kind of a variable resistor, but when we use sinusoidal frequencies, it's what is called reactance, which is the magnitude of this impedance, varies according to the frequency. So similarly, we can analyze this other case, an inductor. This time, to make the calculation more simple, I substituted a voltage generator with a current generator. This current generator will become important later on in this course because at a certain point, as we need an ideal source of voltage, so something that regulates the voltage across two nodes, we will also need an ideal current generator, which is something that makes a current that we want, we can define flowing in a bipole component. So for now, we just say that they can exist. We will need a transistor to do this, and we'll see. Now we take this for granted, we use it, we do something very similar. So now the Constitutive Law that relates the voltage with something else for inductors is this one. It's Induction Law. So the voltage appearing across an inductor is not according to the Ohm's law, not according to the law with the capacitor, but it's according to this. So we have to consider the time derivative of the current flowing in it. If we do the same thing here, so now we consider a current generator, sinusoidal current generator, so we can write this in the phasor notation like this. Then this time we have to compute the derivative of the current. There is also this coefficient of proportionality L, which is the self-inductance of the inductor. Then we end up with something like this. Again, we have to compute a similar derivative. Then we simplify those two things, and finally we get that the impedance of an inductor is again a complex number but different. Now it's proportional, directly proportional to omega. And so just to make a long story short, we can try to repeat the analysis of the circuit at least into two extreme cases. So for omega equals 0, which means for a steady signal like this, so we give a so-called DC current. So if we attach a battery with providing with some circuits a constant current I to an inductor, then it means that this signal is a sinusoidal with a omega frequency equals to 0. Then the impedance of this guy would be 0, and then it means that if we try to calculate the current, I equals V over Z. If this thing is 0, it means that the current is infinitive. So basically, for low frequencies, the inductors are short circuits. We can imagine this because it's just a piece of copper wound in a spiral way. The other thing is that if omega goes to infinitive, then the impedance gets to infinitive. So this thing goes to infinitive when omega goes to infinitive. And so we have 0 current for any voltage. So inductors for high frequencies are insulators. They don't allow any current flowing inside them. And then I just want to conclude this first part by remembering this, the ideal amplifiers. So with these ideas in mind, now we will try to better study this concept.